Okay, so let's get started. If you have a homework 3 to turn in, the pile's up here. So going once, going twice for homework 3. No homework 3s? Okay, so that's it for homework 3s. Okay, so any questions from last time? Yeah.
It's not from last time, it's on homework 3.
Okay, yeah, you can ask questions about homework 3 and whatever. Yeah.
So number 2, it asked us to produce a PDA on the edit distance.
Yeah.
I was wondering if you could quickly go through that.
Okay, so what was this edit distance thing? Oops. I don't want to do that. I want to do this. So we have this ED function, which is the minimum edit distance between W and K. So I'm only going to sketch a high-level overview. So, well, what does the edit distance mean? So what are the edits that we can make? Well, not increment. Right, yeah. So I can insert, I can delete, I can substitute, right? So do we know in advance which one of the 3 that we're going to apply? Or it doesn't really matter the order, but do we know in advance which of the 3 we're going to apply? So could it be possible that I just make no deletions at all? Yeah, it could be possible. So what you can do is exploit non-determinism here. So what you can do is play with the stack by saying, I'm going to insert stuff on top of the stack, and I'm going to guess whether or not I'm going to need to insert or delete something. So think about what edit distance really means. So suppose we have to make an insertion, a deletion, and then a substitution. Does it really matter what the order is? Ignoring the substitution. Well, we're not going to insert and delete the same character. So the order doesn't actually matter. So what I can do without loss of generality is I could have one state that handles the insertion and then non-deterministically jumps to another state that does any deletion that might occur, and then non-deterministically jump to the state that does substitution. And so on the stack is the thing that we're keeping track of is basically the difference between the 2 strings. So it's, yeah, so I can give you the solution if there's enough a consensus from the class of, so I have a solution. I don't remember exactly what it does because I didn't write it myself, but that's essentially what you do. You have a state that you handle the insertion and you non-deterministically jump over. Okay, so it's the non-determinism will help you here, and because we can do the operations in any order. So that's why you can do edit distance. And the reason why, so the question says, if we look at, I'm going to rename it because I don't remember what the name is. So L of K, maybe I shouldn't use K. Maybe let's do N, where the set of strings, something like this, where the edit distance of W and K is at most N. And the question was that for each integer N, it is context-free. So notice, why do you think I put K reversed here? So what if I instead did W with K and no reversal of K? Is this language now context-free, the non-reversed one? No. So what if N was 0? So that must mean it's the same string on both sides. Well, the language, I'm going to call it S, with W, £W, let's say with W in 0, 1 star, is that context free? Come on, guys. Is this context free? What do you think? Do we need to go through a proof of this, of why this is not context free? So what string should I pick for this? To show that S is not context free. 0, 1. So I'll pick the string 0, 1 # 0, 1 for showing that it's not context free, right? What are the two properties of every string whenever we use the pumping lemma have to have? It's in the language, that's fine. What's the other property? Length at least p. Does this have length at least p? No. So how can we get it to length at least p and the same string on both sides of the £? What's a simple way? Yeah, 0 to the p, 1 to the p, £, 0 to the p, 1 to the p. Is that in the language? Yes. Is it long enough? It's only 7:50. We have an hour 40 minutes left. Okay, we got a long way to go. So why would this string allow us to pump out? Well, if we pump on the left side of the £, well, remember, for context free, we can pump anywhere. If we pump on the left side and put more stuff on the left side, then the right side is not the same string because we didn't touch it. If we pump on the right side and put more stuff into it, the left side doesn't get touched, so it's not the same string on both sides. Well, could I pump on both sides of the string at the same time? Instead of just one side, could I pump on both sides? Yeah. Well, what if one of the pump parts contains the £, and I put an additional copy of the string in? Won't I have 2 copies of the £? Yeah. So what is the other case? Well, the other case is that the V part is in the 1s on the left side, and the Y part is in the 0s on the right side. Well, if I put an additional copy in, I'm going to have more 1s on the left side than there are on the right side. And so therefore, we're not in the language. Okay? So the proof of this, essentially this, is in the book, so please look at it, okay? This is kind of scary to me. Please review the pumping lemma for CFLs. Do you think it'll be on the test? That'll probably incentivize you. Yes, it will be, okay? So why do you think I put, so going back to the question I had earlier, why do you think I put reversed here? So I'm not going to answer this directly. Let's talk about the version with W # W reversed, where W's in 0, 1 star. Is this context free? So this one is not CFL. What about this one, the S' language? Well, let's see. If it's W and then the reverse of W on the right side, what do I know about the first and the last character? They're the same. So can we make a grammar for this? Sure. And the way you make it is, I should make a different start variable called not S. I'm going to call it A, and then, well, if it's 1 at the front, then there must be a 1 at the back. So I'll have a rule 1A1, or, well, if it's 0, then it's 0A0. And then when I get all the way down to the middle, the only thing left is a £. So that's the reason why I put reversed here, because by having reversed here, it actually is context free. Whereas if I took the reverse out, it isn't context free. Okay? So if you email me, and because I might not remember, I can post a solution for that question. Other questions? Yeah.
If we take W as 0 raised to power b, so that would be in the string.
So for which language, S or S prime? Okay, so S prime. And so the string W that we pick, so not this whole string, the whole string here, not just each individual part, the whole string, and what is that string?
0 raised to power b, pound sign, and 0 raised to power b.
Okay, yeah, so this string. So, and you want to show that S prime is not context free for that reason. So, can we find a decomposition of this string so that no matter how we pump, we stay in the language? Well, what can we do? If we somehow can pump 1 0 on the left side of the pound sign and 1 0 on the right side, well, if we're putting an additional copy at the same time, then I'll still have the same number of zeros on both sides. So here's a decomposition. If I have U be 0p minus 1, the V part be a single 0, the X part be the pound sign itself, Y also be a 0, and Z be the rest, which is p minus 1 other zeros. Well, no matter what happens here, I'm putting in an additional copy of V and Y in those places. And so therefore, we're putting an additional copy of 0 on both sides. And so we have the same string on both sides. We never leave the language for that reason. So why does, and so then you may be thinking, okay, having this all zeros on one side is not going to help us. What if we picked instead W prime to be 0 to the p, oh, oops, not that, 0 to the p, 1 to the p, like the earlier example, but remember we have to reverse it here. So what if we had this string instead? Well, we can do pretty much the same decomposition with just a single 1 on both sides. So if I have U be all of the front zeros and then p minus 1 of the ones, and then the V part be a single 1, and Y be a single 1 on the other side, and then we can always put an additional copy of 1 in there. So it's I'm raising the number of 1s on both sides the same amount on the other side. And so we never leave the language. So the reason why this string works for S was because of that one decomposition where I'm putting more into the 1s, but I can't hit the other set of 1s. And so I can't get the same string on both sides with 1 reversed. So that's mainly the reason. Other questions? Okay, so what were we talking about last time, or at least starting to talk about? What's there?
Description.
Yeah, descriptions. Another word for this is encodings of machines. So we were talking about encodings of machines. Well, not necessarily machines, but the things we've been studying. Mostly machines, but other things too. And we said that if we have a machine or whatever called M, then the string encoding of it is angle bracket M angle bracket, the right angle bracket. So all this means is some way of writing the machine as a string. That's all it means. It doesn't. We're not transforming it into something. It's literally just a string description. You can think of this like if you wrote a computer program and analyzed the binary where the class, the object actually lives in memory. You can think of that binary string as the representation. That's another way you can do it. But you can do it explicitly. We don't care about what the encoding actually is, as long as we can figure out from the encoding what the machine actually is. Okay, so when we're fed the encoding, we would be able to know what the machine actually is. Okay, so what were we doing with encodings of machines? Staring at them?
We were putting in a tape.
Yeah, we were putting them onto tapes, and were we studying, I think, some problems about given a certain machine and an input, whether or not the machine accepts the input? Were we talking about something like that? A decider for what problem were we trying to solve first? Right. So we were talking about this problem A sub DFA, which is encodings of a machine and an input. So where M is a DFA and W is accepted by M. And what did we show about, so sorry to interject, but note that this actually is a language. Why is it a language? It's a set of strings. So why is it a set of strings? Right, so all of the elements are encodings, which are strings. Okay, fair enough. Okay, so what did we talk about with respect to ADFA? What did we find out about ADFA? It was decidable. So that's what we showed last time. What does decidable mean? You were getting there.
Oh, that halts.
That what halts?
The computation.
The computation for the machine for this language. Yeah. So this says decidable means that there is a Turing machine for this language that always halts. So no matter what input it gets, it always stops at some point. And it says the right answer, obviously. So that's what decidable actually means, and that's what we showed last time. Why is this language decidable? Why is it decidable? So how did we show that? Okay, I don't know how that happened. Let's see. Good, it kept going. Yeah, go ahead.
Because if you have a valid input and then the DFA is always going to end up in the final state, then
yeah, but how do we know that whether or not the input W that is given will end up in a final state? How do we know that it'll go to a final state? Yeah, so that's the thing. The input W, the string to the machine M, it's finite in length. And so we keep track of what state we were in and what character we were reading along the way. And then we're just marching through the input W here. And so there are only a finite number of characters. Well, we have to go back and check in the machine itself what the transition to do is. But the input is only finite in length anyway, so therefore we can actually do this check in a finite amount of time, because all we have to keep track is the state and the character we're looking at. Okay, does that make sense? So we made this high-level description of how a machine would actually do this, how a Turing machine would solve this problem. Okay, and what was the one that I introduced right after this one? Yeah, NFA. So NFA is essentially the same language where M is an NFA instead of a DFA. And W is accepted by M again. Okay, so what do you think this language is? Do you think it's decidable? Yeah, so I claim that it is decidable too. And if we want to show it's decidable, well, we would need to make a Turing machine for it, and we might as well just stick with our high-level description because it's just easier. So if we want to write a high-level description, remember, we have to do this on input MW thing, where M is an NFA and W a string. Okay, so you should note something here. Look at the description of the language itself. It says that and W is accepted by M, but in the on input statement, all I say is that W is a string. Why don't I put that and W is accepted by M? Yeah, that's the problem we're trying to solve anyway. So we don't know yet that W is accepted by this machine M, but we'll determine that here. Well, can we just start tracing through the NFA and figure out whether the input's accepted by it? Or do you think there's an easier way? So what's an easier way? Yeah, convert it to a DFA. Huh. Is there a procedure, an algorithm that converts an NFA to a DFA? Yeah, so we didn't have to use any intuition, remember, of how to do that power set construction, right? We just looked at the epsilon closure, figured out where we can go on a certain symbol, and then did epsilon closure again ad nauseum until we exhausted the input. Well, no, not the input. I mean, went as far as we needed to go in constructing states. So all we really need to do then is convert M into an equivalent DFA D. And then we should say using the power set construction. You don't explicitly have to put that, but it's a good habit to get into of understanding what conversion you're actually using here. I don't know why it's not called power set conversion, but because it really is just a conversion. Anyway. Okay, so we have an equivalent DFA for the same language as the NFA that we're given. Cool. So now what do we do? Or what is a good idea to do? Well, have we already solved the problem of whether a DFA accepts a given input? So that is the ADFA problem. What do they tell you in software engineering classes, like don't reinvent the wheel or something? So do you think it's a good idea to put all the steps in solving ADFA copied and pasted into here? Probably not. So what we're going to do here is run the decider for ADFA on input. Okay, well, this may seem kind of simple, but what input are we going to give to the ADFA decider? Well, we got to give it a DFA and an input, right? So what is the DFA that we're going to give? The D in this case. And what is the input that we're going to give? W. Does that sound kind of silly, why I asked that? I think so. The reason why I'm asking that is that when we're going to get to A sub TM later, probably today, the input is not going to necessarily be the input that we're given. So it's going to change. But here it's really simple. It's just the DFA that we made and the original string input that we're given. Okay, great. Well, does this decider for ADFA always halt? Yeah, why? Well, not just because that, but it's run the decider. What is a decider? A decider is a machine that always halts. Okay, great. So the decider must then say accept or reject because it can't run forever. So if the decider accepts, well, now we got to think a little bit indirectly. So if the decider actually said yes, the DFA said yes on this input W, Now we gotta make the answer of whether the NFA accepted the input W. What should we say here, accept or reject? Accept, because the DFA that we made has the same language as the NFA that we were given. So if the DFA says yes, we should also say yes. Okay? I may be going way too slow here, or am I going too slow, or am I still going too fast?
I think you're good.
Okay, okay. The reason why I'm going at this pace instead of usually faster than this is that most students have trouble in this section, more than any other thing in the class, understanding how to actually do these algorithmic things, and knowing whether to accept or reject here. So the way that you approach these is think about your high-level goal. What are you trying to do? You're trying to figure out whether the NFA says yes on the input W or not. Well, we're doing steps in the middle to deal with DFAs and whatnot, but our goal is still the NFA and the input. Well, note that the DFA has the same language, so whatever the DFA said, we should say the exact same thing. Okay? In some contexts that we're going to get to eventually, we're going to do the exact opposite of whatever the machine actually said. Okay? So sometimes it is the exact same, sometimes it's the exact opposite. Here it's the same, because the language is the same. Okay, and then otherwise, well, otherwise then the decider said, no, we don't accept the input, therefore we're going to outright reject. So this very clearly does solve the NFA problem, right? But what is the final thing we need to check about the machine itself? What is our claim about a NFA? It's decidable. What should we show about the machine to really make sure the language is decidable? Could the machine run forever? Well, if it did, then that would invalidate our decidable claim. So let's at least reason why our machine that we made here does always halt. Well, does step 1 always halt? Yeah, because the conversion between an NFA and a DFA always halts. It's an algorithm. It always halts. And so step 1 takes a finite amount of time. It may take a long amount of time, but it takes a finite amount of time. What about step 2? Does it halt in a finite amount of time? Yeah, because we're assuming there's a decider for ADFA, which always halts. And then step 3, of course, takes finite amount of time too. So therefore, this whole machine takes a finite amount of time. And then therefore, our decidable claim is actually good. Any questions about that? About how we made this machine, how we approached it? Anyone totally lost? Yeah.
If it's like a really, really large input for a DFA, and let's say it does accept, but it takes like a year, it says like, if the decider accepts, accept, otherwise reject. What if it's like before it's made its decision? Would you just
well, the way that the decider for ADFA works is it has to go through the entire input first. So you're right. If we wanted to make this faster, then we can see, okay, are we in a dead state right here? And then therefore, if we are, then there's no point in continuing. And then we can make it faster. And there are ways to actually do this in practice. But as I think I've said a few times here, we don't care about the physical limits of our universe. So we don't care if this takes a Googleplex to the grams number of years. Okay, so it's just how we are going to approach this here. It may be a really long input, but yeah. Yeah, so we may talk about that sort of thing where we actually do care about algorithms running efficiently. Here we don't really care about that, and we may get to that sort of thing if we have time in the end. Other questions though? Yeah.
Yes, this question. How does it know when?
Because the deciders for ADFA, it said accept or reject. So think of like step 2 as a function call. And then you're returning the result from the function that is called. So you're calling this function that returns true or false, you're returning that function call's value, essentially. You're forwarding the work off to this machine, and it'll do the answer determination for you, and you return the exact same answer.
So in this case, that function is the DFA.
Yeah. So it's the decider, the Turing machine for ADFA. And then we just forward the work onto that, and then we get the result, and we make the determination, which is the same determination as the machine before. We accept if the original thing accepted, reject if the original one rejected. Any other questions? Okay, so I'm not going to go into much detail on this one. What about for regexes? So R is a regex, and W is described by R, meaning that the regex can generate that string. So what do you think this one is? Yeah, this one's decidable too. And so I'm not going to actually make the machine for this because it's basically beating the same dead horse over and over. So why would this be decidable? Right, because we can convert a regex into an NFA, and then what do we do with the resulting NFA? Call the decider for a NFA, which we already saw. So you can see now that we're building up this library of problems that we can solve. We started with ADFA, then we got a NFA because we already built the one for ADFA, and then we have one for regexes too. What about regular grammars? Same thing. Just convert it to an NFA and call the a NFA decider. Okay, so the key thing that I want you to take away here is that all of these problems are decidable. All 4, I guess, that I just mentioned. All 4 are decidable. And here's one thing that you should keep in mind, because a lot of students miss this, hint, hint, is this statement right here. So what usually students write is run a DFA on something. Why is that not correct phrasing? What's inherently flawed about that, stating it that way, instead of saying run the decider for? What's that? Right. Yeah, so can you run a language on a string? That doesn't really make sense. We can run machines on a certain string. So that's why you should always say run the decider for blah on some input. Okay? It's just something I see all the time with students. So don't fall into that trap. Other questions? Okay, so let's actually take a small detour. Instead of talking about acceptance problems, let's talk about an intermediate problem, and then we'll get to one after that. So you may think, well, think of a really large class of 355. So I was actually a TA, I think 2 years ago or something, where we had 366 students and 2 TAs for 366 students. And then the previous semester we had 350. So think of the very first assignment where we asked students to make a DFA for a certain language, and then they submit their DFAs, and of course we want to check whether their DFA matches the sample solution, right? Well, what do we know about how many DFAs have a given regular language? How many are there? At least one. It's way more than that. Infinite. So do you think we poor TAs, have infinite time to check whether your DFA matches one of an infinite list of DFAs? Probably not. So you may think, okay, is there some type of algorithm to say, here's a DFA, here's a possibly looking different DFA, and we want to check whether they really are the same language. Even if they're built differently, they have the same language. That may be really useful. So for determining whether you submitted the correct DFA, even if it looks different, it still has the right language at the end. That might be really nice to know. So we're going to look at an intermediate problem, and then we'll see why we're looking at that intermediate problem when we get to the equivalence problem. So the intermediate problem is called eDFA. And the E here stands for emptiness test. So you can think of this as saying, does this DFA accept nothing at all? It doesn't accept any strings whatsoever. So here, we're not testing whether a machine accepts a given input. We're testing something about the actual machine itself with regard to any input whatsoever. So here we're asking about, instead of a DFA and an input W, it's just the DFA itself and nothing else. And in here, of course, M is a DFA. But the qualification is that we want to check is that L of M is empty. Okay, so that's the problem that the intermediate problem that we want to solve. So, okay, any ideas of how to approach this? Well, let's try this. So it won't work. Let's try the empty string, then all strings of length 1, all strings of length 2, all strings of length 3, and then see if, and etc., and see if any of them go to a final state. If any of them do, then clearly the machine has non-empty language, and therefore we reject. Sound like a good idea? No, what's the problem with that idea? It's not decidable. Well, that wouldn't show it's decidable because the Turing machine may take infinitely long time. Yeah, go ahead.
It's supposed to be L of M is empty or not?
So it is equal to empty. Yeah, so the machine I was talking about is checking if it isn't empty. And then that would be a witness to show that it isn't empty because we found a string that works. Well, how would you show that, or how do you think you should show that a DFA does not accept anything? Yeah, go ahead. Well, if there is no way for the start state to reach any final states, if there are any, then can there be any way for the machine to accept anything if you can't reach the final state at all? No. Oh, so if we can find a way to see the start state can reach one of the final states, if there are any, then great. Then we can solve this. Does that sound like a familiar problem? 310 hat on. Any particular problem that sounds like? Whether some node can reach another node? What does that sound like? It's a 5-letter word starting with GR and ends with APH. And then traversal. And then problem. You guys are a tough crowd. Does that sound like a graph traversal problem? What graph traversal algorithms do you know? Breadth first search and depth first search. Well, the graph is finite in this case, so either one of those works. So, well, wait a second. We have a DFA here, and we need to be able to convert it to a graph. Well, what would you do? You have a DFA which has these state things and transitions, and we want to make a graph out of it. Well, first off, what type of graph should we make? Should it be undirected or directed? Directed. Why directed? The transitions are inherently one direction, not the band, the one direction transition. Okay? Well, so wait, we still have states though. So what should we make for each of the states? A node or vertex. Okay, cool. So for this problem, if we're going to make a graph from this, well, first off, we gotta take a DFA as input. So on input M, where M is a DFA. Well, let's actually make a graph. Or a directed graph, I should say. So construct a digraph. So digraph in the graph theory literature just means it's a shorthand for saying directed graph. I'll actually put it here in case you haven't seen that notation before. Construct a digraph called G, where the vertices of G are the states of M. So we're just converting each of the states to a vertex in the directed graph, and any transition becomes a directed edge. And if there are two transitions between the same states in the same direction, then we just collapse them down to a single edge. Because if you can take a transition on input A and then a different transition between the same states on input B, then we can take either one of those to so just make a single directed edge in that case. Okay, cool. So what would we do for this digraph then?
Try to get to one final state.
Oh, okay. So, well, let's see. What kind of algorithms could we use for directed graphs? We have a single source and a single, well, possibly multiple, I guess, destinations to go to. Well, there are two approaches we can do. We can do a breadth first or depth first traversal of the graph, and then we can find the connected component that contains the start state, and if that has any final states in it, then we're good. Another approach you might try is iterate through the final states and then just run breadth first search trying to find that single state, and then try the next final state, try the next final state. Let's do the connected components idea. So find all vertices in the connected component corresponding to the start state of M. And then if the component contains, oh, in fact, here's actually where we're going to see the reverse happen. So if the component contains any final state of M, because either it has a final state in its component or it doesn't. Well, if it does have a final state in that connected component, what does that tell us? That tells us that there is a way to go from the start state to some final state somewhere. And what do we know about the language in that case of the DFA? It's not empty. Well, we're trying to answer the empty question. So should we accept or reject here? Reject, good. Does my tone help in determining the answer of those two? I'm actually halfway serious. Okay, good. So I'll try to do that more often then, to the bemusement of all of you. Okay. So if the component contains any final state of M, then we say no because there must exist some string that the DFA accepts because there's a way to get to a final state. Well, the only other case is that there's no way to reach any final state at all. Well, because there's no way to reach any final state, what do we know about the DFA that we have? It has empty language because there's no way to accept anything. We can't reach any final state. So, of course, we're going to accept here. If I can draw it. Accept. Nice. So this is actually a really interesting problem. Whereas the A, DFA, A, NFA, whatever problems, they're just doing the algorithms we already knew how to do. This is using our graph theory knowledge from 310 to solve a different problem, which is pretty interesting. There's actually a different way that you can approach this. What you can do is, you know that stupid strategy that I talked about, like feed in the empty strings, strings of length 1, strings of length 2, strings of length 3? You actually can cap it, where after this point, you don't need to test any strings longer than a certain length. And the proof involves the pumping lemma. So there is another way to approach this. This is not the only way to go, but this is the easiest way to look at it, in my opinion. But any questions on this machine that we made? Yeah.
What would be like if we make a DFA, then we would know like from making it whether it or not it has a final state or not.
Mm-hmm.
So why would you even need to check this?
Great question. So couldn't we just simplify this to say, oh, if M has any final states at all, reject, because therefore its language is not empty. And if it has no final states at all, then we accept because there's no final state. Is that the same problem? No. Can you give an example?
Final state that's unreachable from the start state?
Right. So what if we had a start state like this that, say, has input A, B like this, final state that is unreachable like this? Yeah. So you're right. It's very, very close. What you can do is you can, so here's a third way to approach this. Delete all unreachable states. So states that definitely can't reach the start state, and then prune all those off, check if there are any final states left. It's essentially doing the exact same algorithm, but in reverse. So it's like we're starting from the states you can't reach, whereas this one starts from the ones you can. But they coincide at the very end anyway. So yeah, so there are other ways you can approach this. Other questions? Yeah.
How would you describe if you delete all the unreachable states?
Yeah, so the problem with that is how do you determine unreachable? Which means you have to run the search algorithms anyway. But it's a different algorithm because here we're not actually deleting the vertices of the graph, whereas that one would. So, I mean, you don't have to delete the unreachable ones, but it's helpful. Other questions? Okay, so what do we then know about EDFA? What can we determine? It's decidable. And so can you give me a brief explanation as to why it's decidable? Well, if all 3 steps take finite amount of time, then we're okay. So does step 1 take a finite amount of time making the directed graph? Yeah, because it's essentially just a copy of the DFA, but you just strip off the character on the transition and collapse multiple transitions if there are any. So that's easy. What about step 2? What's that?
It is finite.
Yeah, it takes a finite amount of time by what algorithm? Say breadth first search, for example. Well, what does breadth first search do? You start with the node you're looking at, and you always expand to one additional node at each point. So no matter what happens, we're always going to consume another vertex of the graph until we have exhausted every vertex that we can actually reach. So there are only a finite number of states in the, vertices in the graph. So each one, we always add 1, so therefore there are only a finite number of steps for step 2. And then step 3 obviously takes finite time too. And so therefore the whole thing takes finite amount of time. Does that make sense? Any questions on EDFA? So let's actually take a break and then come back to the other problem I want to talk about.